Hey there, these are the motion examples, number 1 through number 5. And we'll first talk a little bit about distance versus displacement and what the definition of each one of the two things are. Distance basically is just how far something travels. Um, it's a scalar, and by the word scalar, we mean that it does not have a direction. So if I go from here to my home in Cicero, it's about 15 miles. On the other hand, displacement is how far something travels in a given direction. So it is a vector, and that means it has direction. And so now I would say that I've traveled 15 miles northeast, and that would give me displacement. In the same way, speed and velocity are related. So when we look at speed, we know that speed is how fast something goes, but it's only the speed. So if I drive on 31 towards Kokomo, I would just say that I'm driving 60 miles per hour. I would not give a direction. Velocity, on the other hand, is how fast something travels in a given direction. Now I would say I'm traveling 60 miles an hour north if I'm going toward Kokomo. The equation for speed is just speed is equal to distance over time, and for velocity, we put a little bar above it. That just means that it's velocity. That's how we can tell the difference between it and speed. And it is the change in position over the change in time, or the displacement divided by the time. For the very first problem, you have Ben. So here's Ben. He's watching a thunderstorm from his apartment window. He notices that when he sees a flash of lightning, a bolt, and begins counting the seconds till he hears the clap of thunder just 10 seconds later. We're going to assume that the speed of sound in air is about 340 meters per second. They want to know how far away is the lightning bolt in both meters and kilometers. So for this very first one, we have an average speed of about 340 meters per second. We know that it takes about 10 seconds from the flash until the bang to be heard. If we go back to our equations again, we'll see that speed is equal to distance divided by time. At this point, we can plug all of our numbers in. So here's our speed, 340 meters per second. Our distance is what we're looking for, and we have time on the bottom. In order to do this problem, it's very simple. All we do is just multiply both sides by 10, so just really basic math here. That will make the 10s go away, and at that point, we'll end up with 340 times 10, so you'll just notice that it's just flipped the other way. It doesn't really matter. That would be 3,400 meters. For letter B, they want us to convert that to kilometers. So what I did was I set up dimensional analysis. Ideally, I should have the 3,400 on top of 1 here. But you'll notice that the meters cancel. There are 1,000 meters in a kilometer. That's on your equation sheet. And if I go ahead and do the math, you'll notice that my answer here is 3.4 kilometers. Another thing we can do is just move the decimal place back 3 places, because that's how many zeros there are for meters in a kilometer. And that is example number 1. Example number 2. This one says on May 29th, 2005, Danica Patrick was the first female Indy 500 Rookie of the Year after her 4th place finish. The best finish for any woman in the event's history. Danica completed the race in a time of about 3.174 hours. So she traveled 500 miles. She did that in a mere 3.174 hours. They want to know what was her average speed. So average speed will just be the distance divided by the time. We just plug in the two numbers, 500 miles divided by 3.174 hours, and you should end up with about 157.5 miles per hour. So that's the average speed. She didn't do that the entire time. Remember, she was in the pits going 0, and then down the straightaway she was probably pulling 230, 240 miles an hour. So that's pretty quick. Example number 3. This is a crab, and the slowest animal ever discovered was a crab found in the Red Sea. It travels with an average speed of about 5.7 kilometers per year. They want to know how long it would take the crab to travel 1,000 kilometers. So there's our 1,000 kilometers. We know that the average speed is about 5.7 kilometers per year. We'll use our equation again. Speed is equal to distance divided by time. Plug all of our numbers in. At this point, we can switch the t and the value that we have on this side on the top, that's a little trick that we can use. So this is really over 1, and if we switch them, we're just basically cross multiplying and then dividing all at the same time. At this point, we end up with t is equal to 100 divided by 5.7, and we end up with an answer of about 17.5 years. Notice that we're really not worrying about significant figures here. We did follow those here, but in the end, we don't stick to the rules that we do in chemistry. For number 4, this one is Tiffany, who's opening with a new Broadway show. She has a little bit of limo trouble in the city. She only has 8 minutes until curtain time, so she hails a cab and they speed off to a theater down a 1,000-meter-long one-way street at a speed of 25. The travels take her on and on and on, and you can kind of read the problem to see what's going on. So what we're going to do is let's figure out if she actually makes it on time. There are several segments here for her to travel. The first one, she travels down a road, then she gets to a stoplight and she has to wait. Then she goes down another road, so this is segment 3, until she gets to the very, very end. So let's look at each one of these segments. In the first segment, she travels 1,000 meters at an average speed of 25 meters per second. We need to know how long that took her. So we'll use our equation again, v is equal to d over t. Plug all our numbers in, go ahead and do our math, and we end up with a time of 40 seconds for that first segment. For segment 2, they make it really easy. They tell us 1.5 minutes, but we need everything in seconds. Typically in physics, when we do problems, we'll use the units kilograms, meters, and seconds. And so I call this KGMS, K-G-M-S. So kilograms, meters, and segments, and that's known as KGMS. So if you remember it that way, it kind of makes it a little bit easier. But that's the kilogram, meter, and second. For the third segment, we know that she, well, that's 90 seconds. When she goes down this road, it's a little bit longer. It's 1,700 meters. Her average speed is about 10 meters per second. And if we plug everything in, we get 10 meters per second is equal to 1,700 meters per a unit time. We've got to find that time. So we go ahead and switch the 10 and the t again. We end up with 1,700 over 10. That's 170 seconds. At this point, we need to add all of the times together. So the 40 seconds from the first segment, 90 seconds sitting at the light, which is a long time, and then 170 seconds to go down that final road. So it's 300 seconds. They told us that she actually only has about, 8 minutes for her to get there. If we take the 300 seconds and we solve for minutes, so we know there's 60 seconds in a minute, so 300 times 1 is 300 divided by 60 would be 5 minutes. We know that she makes it. For part B, they wanted us to do a distance versus time graph. So if you do that, just sketch it out. You don't have to use graph paper. You'll notice that we go from 0 to 1,000. And we do that in a short time of about 40 seconds. And then from 40 seconds up to 90 seconds, you'll notice this is our waiting time. And then we travel again all the way up to that 300 seconds. So from the 90 all the way out to the 300 seconds, we travel that other distance. So this just kind of shows you her speed. Really fast here, no speed here, and then a little bit slower because the slope is not as steep on this part. This is the last problem. This is example number 5. And in this example, it says Grace is driving her sports car at 30 meters per second when a ball rolls out into the street in front of her. So she slams on the brakes and comes to a stop in about 3 seconds. They want to know what is the acceleration of the car. So far, we've only talked about speed and velocity. At this point, we're going to talk about acceleration. Acceleration is basically just speeding up or slowing down. So either of those will work. This little o here means original speed. So the little o is original speed. The final speed that we have here is 0 because she comes to a stop. So anytime you see the f here, that f just means that is the final speed. We know her original speed, we know her final speed, so definitely she's slowing down. We call that decelerating. and the time it takes for that to happen is about 3 seconds. And they'd like for us to find her acceleration. We'll just use the equation acceleration is equal to the final speed minus the original speed divided by time. Always write down which one is which. There's a big difference between 0 minus 30 and 30 minus 0. So here we have 0 minus 30 divided by 3. Yes, that will be a negative acceleration, which just means that you're slowing down. So that's negative 10 meters per second squared, and that would be her acceleration. The negative sign here just really does mean that she is slowing down. So here she is slowing down. And that is the end of examples 1 through 5 for motion.